Okay, so welcome everyone. Thank you for being here. So my name is Aurelien Didier. I work at Artal Technologies on the Time4Sys project, which is an open source project. So Time4Sys aims to help system engineers to analyze the schedulability of their real-time system. So I will try to explain what are real-time software systems and what is the schedulability. And after I will show why we have developed Time4Sys to answer to the problematic of these domains. So basically, self-driving car are real-time software. As you can see, when for a human driver, the time taken between the moment when you see an obstacle and the moment when you brake, which is called the reaction time, had to be less than 1 second. So for a self-driving car, we want to be at least at this time. We don't want that the time between we detect the obstacle and the time we brake take more than 1 second, or it can cause to a crash. So we can represent this situation with this diagram. So both cases are quite similar, but when a human driver can't react fast enough for some reason, it can cause a crash, and for a self-driving car, it's exactly the same. So that's why you need to be sure that the system will react fast enough. So to be sure that the system will react fast enough, we have to study what happened inside the processor. So the study of what happened inside is the study of how the tasks are executed on the processors, and that's what we call the schedulability. So to study the schedulability of a system, we have to evaluate some criteria. Like it depends on which scheduling policy we are using. So the scheduling policy is the algorithm to choose in which order the tasks are going to be executed on the processor. And there are other criteria that can influence the schedulability of our system, like if there is precedences between the tasks, or if the tasks are preemptive or not. So a preemptive task is a task that can be interrupted by another task of higher priorities. So all of these criteria impact the schedulability of our system. But on some system, we have to do this analysis, because as for the self-driving car, if the timing constraints are not respected, it can cause death of people, or for the space mission, it can lead to high cost if the mission fails because of timings that are not respected. So that's why in some cases we have no choice but to study the analysis of our system. The problem is that as there are more and more, as the criteria of our analysis are more and more complex, the analysis complexity is growing too, and the real-time system itself are becoming more and more complex. For example, in the last aircraft, if we compare the number of buses in each aircraft, we can see that it is increasing exponentially. So the complexity of the analysis study explodes too. So the people who work on this subject are mostly system engineers which work with real-time specialists. So at the moment, to cover their needs to capture the real-time information, they can use AADL or UML MART. And to analyze the systems, there are already existing tools like MAST and Cheddar. But we will see that it's still complex because, for example, before Time4Sys, you start with designing your real-time system using UML MART. But after, well, you have to choose a tool to analyze or simulate your real-time system. So you have to see in which case you are, what are the criteria, can some of the available tools be applied for this system? Because not all the analysis tools need the same context. And after that, so you decide to use, for example, Cheddar. You have to enter the information in Cheddar, so the same information that you had on your design model. And once you have, so it's a bit complex because you have to re-enter all the information in a different way. So you have to know the tool before using it. And once you have that, you can maybe simulate the schedulability of your system and see if everything is okay. But if this kind of analysis or simulation tools does not give you the right answer for your problem, you have to choose, and maybe this time instead of simulation you want to use analysis. So you have to switch the way of expressing your real-time system for something, for example, like AADL, and you have to translate it in the right syntax. So this is just one transaction. So if in our little example we have already five transactions between the tasks. So it can be really long to give all the information about your system, and then you start to becoming crazy because you have already done that with the simulation tools before. But if you succeed, then you have the result of your analysis, and you can see if your software is meeting the deadline, because you have here the worst case response time, which was interesting you. So, and after that, you have to compare the result of this with your original model, which is maybe not easy because they used a different way of expressing the real-time constraint. So it's really complex. You have to know many tools, what are the criteria to be used before using them. So since it's too complex, the system engineers and real-time specialists, some of them use Excel tables to study that, but they have to, in order to have simple algorithms, they have to make really pessimistic assumptions. So that's not really accurate. And so the idea with Time4Sys, so Time4Sys is the result of the WAUNA collaborative project which involve partners such as Thales, which give us a use case from the Avionics and the space industry, and ClearSci, which give us use case from the railway industry. And we have worked, so at Artal, we are specialized in modeling technologies and simulation, and real-time at work is more oriented for real-time system and real-time problematics. And the LIAS and INRIA are two French laboratories specialized in real-time too. So the idea of Time4Sys was to make a bridge between the existing system, the existing modeling technologies, such as, for example, Capella and or AADL or UML-MARTI, and to transform this information into a Time4Sys meta model, which can be used by the existing analysis tools such as Pegase or MAST or Cheddar or Romeo to get the results, and after that to re-inject our results into the Time4Sys meta model and in our original design tools. So how it happens with Time4Sys? So you start with your original design technology. For example, here we have extended Capella to add real-time information. So instead of just designing the architectures of your system with Capella, you can add timing information. For example, in this scenario diagram, you can describe how your events will trigger the task. Are they periodic or sporadic or things like that, to describe what will be their periods. And after, you describe what are the duration of your task, how the tasks are linked between them, which task will trigger other task, and you can also define the end-to-end constraints. And once you have this tool, you can once you have these models, you can transform it into a Time4Sys model, which give exactly the same information, but in the Time4Sys way. And once you have that, you will study the context of your system. So it means that you will evaluate what is the architecture of your system. Is it monoprocessor? Is it multiprocessor? Are your tasks preemptive or not? And depending on the context you are on, you will see which schedulability tests are available for this system. And if you can use a schedulability test, you can see its results. So if it's a simulation, you can see the result with. So here it's a result shown with timing graphics. So this part is not open source, but there is another one in Time4Sys that you can use. And this part is the result seen with MAST. And you can see the response time of your task that were designed with Time4Sys. So in the first part, we will focus on Time4Sys. So Time4Sys is based on is a meta model based on MART, UML-MART. But it didn't embed all the meta models defined in UML-MART. We just took the parts that are interesting for schedulability analysis. But since it's too complex, we don't have access to everything when we are creating our model with Time4Sys. So the idea was to, for those who don't already use Capella or AADL, we wanted to provide a simple way to create a real-time the real-time of the design of the system. So depending on your context, you will have this simple palette that will help you to create your hardware resource, the software resource, and the steps that are going to be executed. And if you are in another context like Arink 653, you can have another layer that will give you other tools. And when you will use the tools of the Arink layer, your design will be compliant with Arink. So this part gives a simple way to create your diagram with Time4Sys. So now we have seen that we can also design it with Capella. So we have extended Capella to add real-time information. So if you start with a normal Capella model, when you switch in the Time4Sys layer, you will see that your component and functions are grayed. And when you add real-time information to them, you will see that they are colorized. So it means that you have described the real-time behavior. And after that, you can choose to add them in a scope. So the scope will help you to determine which parts you want to analyze. So here we can analyze all our model or just focus on this part. And after you can represent also the real-time behavior in a scenario diagram like this to add a constraint on your execution task. And with the Activity Explorer extended for Capella, you can transform your Capella model into a Time4Sys, or you can directly launch the analysis or simulation without seeing the intermediate step, which is Time4Sys. So now I will explain how the model checking part works. So each analysis tools need a certain context to work. So I will check in which context is my model. So a tool is linked to a context, and a context is a set of rules. So if my context is okay, I can launch my simulation tools. But if it's not okay, I want to see which rules are not respected. And if I know a way to correct that, I can transform my model and try to analyze my context again to see if this time there is an existing tools to evaluate my model. So, for example, if my model is, if I am in a certain context, so here this context is accepted, so I can launch the real-time analysis test 4 to evaluate my model. But if it were not in this context, I will see which rules are not okay. So now I will show you the result. So as I was saying, we have two ways to visualize the result of our simulations. So this part will be open source, so you can use this one, and this kind of results are done with timing graphics, which is not open source. Or if you were launching a simulation, you can see the result in the tools that you have used, or you can see the result in your Time4Sys diagram. For example, here you see that your end-to-end flow took 357 seconds instead of the 400 deadlines that you fixed. So both of those cases are okay. So here we can see that we can go from a Capella model to the result of the simulation or the result of the analysis just in one click. But after we have to re-inject the result of our result inside the Capella model. So at this moment, it's not already implemented within Time4Sys. What is done is that you can see the result of your simulation, which are stored in a trace model inside Time4Sys. You can display them on Time4Sys with a result layer that will allow you to do that. But what we are not able to re-inject in a Time4Sys model is the result of our analysis, because analysis really depends on the tools. So we have to define the result meta model to be able to interpret the result whatever the analysis tools chosen. And the last part that is not implemented yet is this last re-injection, because once you have our results in Time4Sys, we want to see them in Capella in order to hide the complexity here. So we already know how to go from Capella to Time4Sys with coevolution, and coevolution gives us a trace between the source object and the target object. So we know that we have links between them. So, but there are no API to re-inject the result. So we are working on that. And the last part. So here as I was showing you earlier, if your context is not yet accepted, there are transformation of your model that will give you a more pessimistic model. Like, for example, you can propagate the activation of your task. So this will simplify the analysis of your model, but we would like to be able to transform your model without any manual interaction. So the idea is to analyze your model, see which rules are not respected, and depending on the rules that are not respected, we want to know which transformation are available to correct those rules. So what is yet to come in Time4Sys is a Papyrus with real-time connection. So the good things of buying open source is that we have started to communicate on Time4Sys, and the people who are developing Papyrus have said to be interested in developing a bridge between Papyrus real-time and Time4Sys. We also are working on the implementation of Romeo analysis tools. So Romeo is a tool that used PetriNet to analyze the schedulability of your model. And the last part that interests us is to have a parametrics analysis. So, for example, we would like to be able to set a period to X or another period to Y, and try to analyze it with Romeo or imitator, and see what is the condition on X or Y, so that makes my system schedulable. So, for example, I would have as a result X must be superior to 17. And so we are also using a lot of open source technologies. So for Tidal, which is a viewpoint for Capella, we use Capella Studio, the semantic browser, and coevolution to make the bridge between Capella and Time4Sys. And for Time4Sys, we are using Cyrus, the Activity Explorer, and the Contextual Explorer. And for the analysis repository, we are using OCL and Zest. And so thank you for your attention. I don't know if you have any questions. Yes? No, I don't know yet if they are starting to implement it. I just know that they are interested because they have talked about with Thales about that, and they were thinking about making their own connection. So I'm not sure that they will use the same technologies as us, but okay. No, so at the moment we have worked on Tidal with Thales only. We have developed it for them. They had some specific specification, but we don't know if it will be possible or not to open source it later. At the moment, they are evaluating it inside Thales, and they will give us feedback after, and maybe one day it will be open source, but at the moment it's not sure. Okay, so thank you everyone.